Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 64th Project Euler problem. As always, I will link to the problem and my repo in the description. Let's dive in. Problem 64 is odd period square roots. All square roots are periodic when written as continued fractions and can be written in the form square root of n equals a of 0 plus 1 over a of 1 plus 1 over etc. For example, let us continue the square root of 23. Square root of 23 equals 4 plus the square root of 23 minus 4, which is equal to 4 plus 1 over square root of 23 minus 4, which is equal to 4 plus 1 over 1 plus square root of 23 minus 3 over 7. If we continued, we would get the following expansion. Square root of 23 equals 4 plus 1 over 1 plus 1 over 3 plus 1 over 1 plus 1 over 8, etc. The process can be summarized as follows. All of that. It can be seen that the sequence is repeating. For conciseness, we use the notation square root of 23 equals 4, 1, 3, 1, 8 to indicate that the block 1, 3, 1, 8 repeats indefinitely. The first 10 continued fraction representations of irrational square roots are, and then it lists them, and you might notice that the square root of 9 is missing because the square root of 9 is simply 3, so it doesn't have one of these periods. Exactly 4 continued fractions for n less than or equal to 13 have an odd period. How many continued fractions for n less than or equal to 10,000 have an odd period? Okay, so this is going to be interesting. A hard part is going to be determining what this period actually is. So let's go ahead and get started. Or at least thinking about it. Okay, steal our favorite little timestamp printing. Okay, so our algorithm, starting with 2, go through an equal limit. For each n, calculate continued fraction period if period is odd, increment count. Okay, so the algorithm here, relatively simple-ish, you know, if you ignore this part, I guess. It's easy to write in a comment, I should say. So let's start with limit is equal to 13. And then for n in range 2 to limit plus 1. Again, so we can get that so we can get that end equal to instead of less than, and then count is going to be 0. This is just if the length of the period mod 2 does not equal 0, then count plus equals 1, print count. So I'm starting with 13 for a reason, and that is to try to make sure that I'm getting the correct answer. So, how do we go about calculating this continued fraction period? That's the hard part, right? So we can see for square root of 23, they're doing 4 plus square root of 23 minus 4. And it's not a coincidence that they chose 4 here, because for the square root of 23 is 4 point something something something. I don't know for sure, but it's less than 5 because the square root of 25 is 5. So they have 4 plus square root of 23 minus 4. And then in order to convert that to a 1 over fraction, they have 1 over square root of 23 minus 4. And then 1 over the square root of 23 minus 4 is somehow equivalent to 1 plus square root of 23 minus 3 over 7. And I'm not really sure how we get there. In particular, how do we get that 7? Because obviously we could just flip it again. But that's the part that doesn't quite make sense to me. Because, like, how do we know that it's a 7? So the square root of 23 minus 4 is whatever the fraction is. Let's go ahead and okay, so it's 0.7958, etc. Let's go ahead and say 23 divided by 4, which is equal to 5.75. So Yeah, I'm still not quite understanding here. And it's this part where it's like, how do we switch it out? That doesn't make sense to me yet. So let's go ahead and Google how to calculate continued fraction. Okay. That looks more like it. Okay, so finding the continued fraction for square root of 5. Square root of 5 is 2.23 or something, and a of 0 is the integer part, which is 2. So then we subtract a of 0 from square root of 5 and take the reciprocal. That is, we calculate 1 over square root of 5 minus 2. If you're using a calculator, this comes out to 4.23 or so. Then a of 1 is the integer part of this, which is 4. So square root of 5 is 2 plus 1 over 4 plus 1 over ... Okay. So going back to our square root of 23, if we do this same thing, the a of 0 is the 4. And then square root of 5 minus 4, or the square root of 23 minus 4, and then 1 over that. To get that, we take our 4.23 and take the reciprocal, as we calculate 1 over 4.23 minus 4, which is equal to 4.23. Okay. Okay, so when we have the negative, okay, okay, so let's see, I saw one of the comments in there saying something about, like, it'll be double when we figure out the end of the period. So that's good to know. So whenever we hit an a of n that is equal to a of 0, or equal to twice a of 0, then we know that we've hit the end of the period. But that doesn't really answer how we get to swapping this stuff out. So let's see if we have an easier, a different. Okay, so this one's a little bit looks easier to read. Okay, this doesn't actually look helpful though. Okay, so that's not what we need. Okay, I think that's just going to confuse me more. So I'm curious how we get to flip this to... Like, how does 1 over the square root of 23 minus 4 equal this? So 1 divided by square root of 23. Nope. Where does the 7 come from? Like, that's what I really want to understand, is how do we get to this 7? So the reciprocal 1 over square root of 23 minus 4 is equal to this 1.2, etc. Which, that part's fine, we can take out the 1, but how do we know that the remainder is equal to this other thing? I suppose, although the precision won't be quite correct, we can just continue doing 1 divided by answer. Let's see how far that gets us. So, continued fraction period. First, we want our a of 0, and I'm literally just going to call it that. and that is going to be n to 0.5, but converted to an int. Okay. And then I'm going to say previous A starts as A0. And then while, or just A equals A0. I don't quite like that either. A equals 1 divided by, let's see, I'm just going to say root is equal to this. And then A0 is the integer version of root. And then it's going to be 1 divided by root minus A0. Right? 1 minus square root of 23 minus 4. Or 1 over square root of 23 minus 4. Okay. Okay, that should work. And then while int a is less than 2 times A0. Actually, I'm just going to say while true here, making it effectively a do while loop. So while true, if I'm just going to do period dot append a, so going to be one of them. Actually, if, just because we're starting with, we're going to hit 9. If I'm just going to say if a is 0 is equal to root, continue. Just to try to skip, like, the ones that are not irrational. Okay, so then if it is irrational, we come in, and then we do that. It's 1 over root minus A0. Oh. We actually just want to append integer of A, which we probably want to pull out anyway, so an equals int of A, and then we subtract and divide 1. just going to put if an equals 2 times a0 break. Otherwise, we go on and we calculate a once more. So a is equal to 1 divided by a minus a over a of n. Okay, so I think this will work. Let's see if it works for 13 and gives us an answer of 4. Not 100% confident in my math here. Okay, so it gave us an answer of 4. Let's go ahead and see if we up that to 23. So I'm not entirely certain of the correct answer, though. So I just kind of want to make sure that 23 gives us the correct period. I'm gonna just say if equals 23, print pound 4. Let's go ahead and up this to the 10,000. It will not take very long to run whatsoever. Alright. I don't think. Maybe it will. Finding the correct answer for square root of 23. Okay, so it is taking a little bit of time to run, but that might not be a problem. Found an answer. It was within our time limit. Let's see if it is the correct answer. I have a feeling it might not be, but let's just find out. It is not. Okay. That's fine. Based on a little bit of the research that I did, it seems like the square root of 139 might be a problem. So let's just go to Wolfram Alpha. Continued fraction for square root of 139. Okay, so now let's have the program print out what I got for 139. Got the correct answer for 23, so that's not nothing. Okay, so that's clearly... I forgot to change that part. Whoops. That's clearly not the correct answer. Let's see, we got 131... 13137112111. 13137112111. 2117313 122. I'm going to have to make it so I can see both of these at once real quick. Okay. 1313711 1211 211 7313 1, and then I got 12 instead of 22. So Let's see. Not entirely certain how it would have gone about getting 12 instead of 22 there. Okay. Okay. Just gonna go here real quick. 1 divided by... Can I not paste this? Cool. 0803787 787 802593 Okay. So it's not like it's doing math wrong, which isn't surprising whatsoever. Okay. So I'm getting 12 and I should be getting 22. How? I'm guessing I'm getting other ones wrong as well, just that one in particular is very much not working. I wonder if it's because of it being a float, and floats being slightly imprecise. But obviously it's working for a bunch of other numbers, so I'm not quite certain what is wrong here. Let's see. Okay. So I think this one's a little bit confusing. So we floor square root, and then x is equal to 1 and y is m. I'm not quite sure how that is working. Floating point arithmetic will almost never suffice. Cool. Okay, so in this one, it's doing that. That's a little bit confusing code to read, isn't it? Okay. Okay. That doesn't look like quite what we want. Okay, so this one recommends using decimal because it is more precise. So I'm gonna try that. And then so just kind of translating this here. There we go. Let's see if that gives us the correct answer for 139. It did. so maybe it'll give us the correct answer altogether. Let's double check that that is in fact the correct answer, actually, because I'm paranoid. Cool. Okay, so it is taking a bit. Let's go ahead and delete the printouts here and just restart so that we have an easier way of telling how much time it takes. I think it is going to take a little bit longer now, but it should still be within our minute. But we'll find out. Giving it a little bit of time to just run through. Okay, I think it might be taking longer than a minute now. Yes, it did take longer than a minute. It got a different answer, and I think that might be the correct answer, but let's see if we can make it take less time by dropping the precision down to 50. Just to see. We did still get the correct answer for 139. So I think we might still get the correct answer for everything else. But I want to make sure. While that's running, to see if we can get it running in under a minute. Let's see whether this is the correct answer. I have a feeling it will be. Oh, it was not the correct answer. So something else is going wrong. Okay. I wonder if I need to increase the precision instead of decreasing it. Okay, yeah. Let's bump it to a precision of 200. That will to make it take a longer run, I think. But it should only take a couple of minutes. And obviously we're not hitting our time limit of 1 minute here. So something else is probably the correct solution. But this is getting us closer, I believe. If this does not give us a different number, not the 2580, but a different number instead, we might have to go back to the drawing board on this one. Though, we've got to be pretty close. It's got to be on the extremely long sequences that we're failing. kind of want to print out a bunch of the periods, especially the ones that are particularly long, just to find out whether they're correct. But since we're dealing with literally 10,000 numbers, it's going to not work, I think. Okay, so there, like I said, that took a couple of minutes, but we still got the 2580, which we know is the incorrect answer. Just double checking. Yeah, not the correct answer. So I think what we are going to end up needing to do here is maybe print some of these out and see. So that makes the output very large, but maybe we will be able to spot something obvious that is incorrect. Not while it's printing it out. So give that a minute, go through some things. We're not going to be able to figure this out, I don't think, actually. I think it's going to take up too many lines. Okay. I'm gonna say if length is greater than 20, print it out, otherwise don't. I don't appear to be able to interrupt this. I don't know if Wolfram Alpha will give us all of that, but let's find out. Okay. Okay, so this only goes up to 102. It's not quite. Wolfram Alpha is only going up to 40. Let's see. There we go. Okay, so square root of 1 is just 1, square root of 2, 1, 2. Okay, there's 139. And we can kind of see that maybe 151 is one where it's a problem. Okay, that took an obnoxious amount of time. Let's, 900,997 is one where it seems likely we got the wrong answer. Could be wrong, but seems likely. Okay, so 165, 111, 21, 111, 21, 114, 75, 222, 16, 449, 12, 115, 110. And then this is wrong. It should be a 4 according to this list. So I'm getting the wrong answer there still. Let's up the precision to 1000 and see if that starts getting correct. What? Not what I meant to push. Okay, so now it should take a bit longer, I think. Especially since it's still printing out all of these different values. And we really are not going to be able to tell, and we're not going to be within the time limit here doing it this way. So there's probably some better way of doing this. But let's just see how close we get. Of course, we could do this somewhat differently, but, and some of these are quite lengthy. Like, we could go take these answers and count it up that way, but that's hardly in the spirit of the problem. So I'm just continuing to let it go for right now. Should probably reduce it to like 1,000 instead of 10,000 for the next round. This is the one we got wrong, and it's going to be the easiest to check whether we got it right. Where are we? We're still getting some very, very large numbers here. So I don't think that's quite right. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 24, 25. So I'm going to bump this up to 25, because that's where it last failed, so that we're not printing out quite so much next time. goodness. Still have quite a ways to go here. But we're on 7,000. I think I saw 8,000 something go by. Yeah, I definitely saw an 8,000 something. So we're closing in on it, but still. I'm gonna go ahead and bump that up to 50 just to see, because we're getting way too many numbers on the ones we get wrong. So next time we run this, it'll take a lot less time, I think. Almost done now. I saw what 9177 flip past. Almost done. Still getting the same answer, so something is not right. And then this is still failing in the same place where it's getting a 3 instead of a 4 here. Let's just run it again now that we've drastically reduced the space and see if we can figure out what's going on. Okay. So 991, we're getting far too many numbers, I think. Oops. 991. Okay. So we're getting 2, 12, 10, 2, 2, 2, 1, 1, 2, 6, 1, 1, 1, 1, 3, 1, 8, 4, 1, 2, 1, 2, 3, 1, 4, 1, 26, 4, and then 24 instead of 31 right there. Okay. Oh. Should also use the context. Let's go back to that precision of 100. Whoopsies. do that there too. Let's see if that gives us... Okay. So 991 now has 2, 12, 10, 2, 2, 2, 1, 1, 2, 6, 1, 1, 1, 1, 3, 4, and 8, 4, 1, 2, 1, 2, 3, 1, 4, 1, 26, 4, 31, 4, 6, 20, 1, 4, 1. Looks like it is the correct answer now. So that's a good sign. Can go ahead and not print that out anymore. Go back to our limit of 10,000 and see if we can get the correct answer. Now, it might still take longer than our time limit of 1 minute. In fact, I would be shocked if it didn't. I am shocked. Let's see if it's the correct answer, though. Here's hoping. Nope. No, it is not. Something is still wrong. Let's up the precision again and see if we get a different answer. Or let's not up the precision yet. No, actually, I'm going to. I'm going to up the precision. I'm going to run it again and see if we get a different answer. What this tells me is that when we get the correct answer, it actually takes less time because we break out faster instead of finding all of these other numbers that we don't need. Okay, increasing the precision did in fact decrease the number. So maybe that is... Okay, there we go. That is the correct number. So really the difficulties in this problem ended up being doing the math. Like I called out right at the beginning, that calculating the continued fraction period is the rub. So I ended up using this decimal with a precision of 1,000. Number maybe should be arbitrarily large, I'm not sure. And then using the context for this decimal thing to do every single piece of the calculations so as to not lose precision, so as to actually find the correct periods. And then once we were finding the correct periods, all we had to do was go, how long is this period? If it is of odd length, then we increment our count. If it is not, we don't. And then that's how many of them have a periods of odd length. So I'm gonna go ahead and call it there for today, and I will catch you in the next one.